Hello everyone, my name is Alexis King. Some of you may know me already, some of you may not. But I've had the opportunity for the past couple months here at Tweag to work on optimizing the compile time performance of GHC, the Haskell compiler. And one of the things that has come up a number of times while I've been working on this is that people don't have a super great idea about how it is that I actually optimize a Haskell program and how I'd recommend that other people optimize a Haskell program. And of course, that's a really, really broad subject. And it's very, very easy to, I think, get the wrong idea and to sort of find one way to optimize a Haskell program to think, yes, this is the way to optimize a program. But that's not the case. But it's very challenging to get a good understanding of what the process is actually like because there's so many different moving parts, and it can be a very abstraction breaking thing trying to understand the performance of something because you really have to understand how it works internally. So one of the things that I would really like to do today is to provide just kind of one example that's not too large, it's relatively small, of optimizing a Haskell program in some particular way that really focuses on a particular approach, which in this particular example is going to involve looking at GHC core. So I have this little example, which was very, very graciously given to me by Sarah ZRF. She goes by on Twitter. So shout out to her. But I've had this example for a little while, and I've wanted to put together a little video or a stream of kind of optimizing it because I think it really is a very wonderful illustration of what I'm trying to talk about. So there's a little program right here, and it has two, and to be honest, what this particular program does is not actually going to be enormously important to this video, but this is a little library that she was working on at one point for simulating differential equations, systems of differential equations. And so this has a little program that I guess just simulates a sine wave, and there's two implementations of it. One of them is written in this very direct style, and again, I'm not really going to go into exactly what it does because it's actually not super important. And then there's this other version of it which does the exact same thing, but it's written using this arrows DSL. And this is much, much nicer to look at and to read. But if you benchmark the two of them side by side, then you'll find that the arrowized version takes a little over 5 times as long as the handwritten one. And I've already run this benchmark here so that you don't have to sit and watch me run it. But this is, it's not a huge difference, but it is a non-trivial difference. And so she was asking me at one point, what can I do to improve the performance of the sort of more nicely written one? Because again, this is much nicer to write. And it's not super obvious how one would go about doing that. There's many different things that could be going wrong here. But the basic sort of core aspect of this is that there's this implementation module here, which defines this OD data type. And again, I'm not going to go into too much detail about everything that's going on because, for one, I didn't write this code. And, as interesting as I'm sure it would be, it's not super material to what I'm going to be talking about. So what I ended up doing while I was working on this is I decided to start, because it's such a small example, by looking at the GHC core that gets generated by each of these two examples. And in fact, I created an even simpler example right here, which is just the identity function, or the identity arrow in this case, and just to kind of take a look at what code actually gets generated here. So if you don't know what GHC core is, that's fine. I'm going to explain it. But let's just start by taking a look, because I think that will be the simplest way to get an idea for what I'm talking about. So I'm going to enable some GHC options here. The first one is going to be this dump to file option, which is just going to say we're going to turn on some other options that cause GHC to dump out some debugging information. And we just want that to be dumped out to a file rather than just spewed into the terminal. And specifically, I'm going to enable this dump simple option, which it's a little bit confusingly named, but this is really going to be dumping the GHC core. So I'm going to save this call project local file, and I'm going to build the project, and I'm specifically just going to build a library so that we don't need to, now it's saying that everything is up to date because, well, let's just delete the new style directory and rebuild. GHC's recompilation avoidance. Actually, that might be Cabal. That's not rebuilding that. It actually makes sense. Normally, you don't want everything to be rebuilt just when you change that flag. But anyway, this is going to be dumping the GHC core. And GHC core, for those unaware, is one of the many intermediate representations that GHC uses when compiling a Haskell program. And so it looks like this. And as you can see, it's very, very verbose and it's very noisy. And this is just the core that gets generated by this one 17-line Haskell module. And it's very, very verbose because there's a lot of internal information that is included in GHC core, which GHC uses when optimizing the program. And one of the things that's interesting about GHC core is that it's an explicitly typed intermediate representation. So a lot of internal compiler representations are not statically typed, and including some of the ones that are sort of later on in the pipeline in GHC. But core is where GHC actually does most of its optimizations, and it is a explicitly typed intermediate language. What this means is that we end up with this enormous quantity of type annotations, which really, and coercions, and I'm probably not going to go into what a coercion is right now. You can look it up if you want. Maybe I'll talk about it at some point. But it's not very important to what we're actually trying to look at. So in order to actually illustrate anything useful, I'm also going to turn on a couple of additional flags here to suppress some of the information that we don't actually need. That's just going to be obscuring what we actually want to look at here. So there are these suppress options. And once again, I'm going to, let's just do clean and build. So let's take a look again. And we're going to look at that same module here, this dump simple file. And, you know, this gets buried in some long path, but you can find it. It's just in, I mean, most of these directories only have one thing inside them, and then it just gets put into a directory that's the same name as your sources directory here. So take a look at this file, and now it's still a lot, but it's much, much smaller. Before it was thousands and thousands of lines, and now we're only looking at about 500 lines of core. So now we can actually take a look at the core itself and familiarize ourselves with what's going on here. So core, one of the things that's really nice about it as a Haskell programmer is that it looks a lot like Haskell. Of course, the variable names are randomly generated internal names. So you know, those aren't super obvious, but once you kind of get past the fact that things are named things like WW1_SOZZD, it actually looks quite a lot like Haskell. There's pattern matching, there's case expressions, there's lambdas, there's lets, there's an explicit let rec for recursive lets. Everything's a little bit more explicit, but it still looks very similar to Haskell. And there's a little bit of additional information here, annotating some of these bindings. But for the most part, we can ignore that and just focus on the actual code. So there's a decent amount of code that's generated here. But what we explicitly want to do is compare the amount of code that gets generated for this direct version, which again is this simple version that was just handwritten, with the arrowized version. And if you look at the scroll bar here, it's very, very small. In fact, my editor doesn't even want to syntax highlight it because it's so big. You can see that there's 8,000 lines of generated core. Rather than just the about 500 lines of generated core that we got from this direct style implementation. And so that's a good indication that maybe one of the reasons that this nice, or not this module, this nice DSL, Arrow DSL, is appreciably slower is that it is just generating a lot more code and presumably less efficient code. So how can we actually get an understanding of what's going on here? Because that's just so much core that, frankly, it's just not very illustrative. If we try and figure out what's going on here, it's not going to tell us very much. So that's why I created this simple module here, which is just exercising. This is not ID on functions. It's the ID that's a member of the category class. And so this is specifically the arrow ID, and just a really, really simple arrow, which is literally just composing the identity arrow with itself several times. And if we have an efficient implementation that's getting optimized well, this should mostly all just get eliminated by the optimizer, because composing the identity function with itself should just give you back the identity function. But if we actually look at the code that gets generated here, if we look at this simple arrow output, you can see that we're still getting quite a lot of generated core. And this is a pretty good indication that something is going wrong. Don't know exactly what that is, but there's some way in which GHC is not optimizing this particular program as well as it could. Now, in many situations, it would actually be very useful for us to take a look at the core and understand exactly what's going on here. But when I was taking a look at this particular example, I didn't find that very helpful. There's a lot of transformations that GHC is actually doing on this particular code to try and improve it, but it just doesn't end up resulting in anything particularly nice. And so what I wanted to do was really understand why this specific example right here was not getting compiled in the way that I felt like it should be. And these things should just sort of cancel out, and we should get something very simple. And so on this particular example, one of the reasons I think it's so useful and such a good illustration is that I'm actually going to go through this by hand, and we're going to kind of work through what the GHC optimizer does given this particular program. And so we're going to pretend to be the GHC optimizer. And I think that can give a really good intuition for what's actually going on and why GHC is struggling with this particular program. Sorry, I realized I misspoke a little bit. It's not this particular program. It's actually this other module here that we're going to take a look at, which is the problem case. And even though it generated such an enormous amount of core, it's actually going to be useful to just kind of walk through this particular example. And again, one of the things that I really like about this example is that it's not something contrived that I just came up with myself. This really was when I was looking at this, and I mean, this was almost a year ago now, but when I was looking at this was my first time looking at this program, and this is really what I did, although of course I'm going to be going through it a little bit faster than I actually would have done it, just to make this a little bit more interesting and not waste all your time with me staring at core. So if we want to understand what this particular program does and what GHC does to this particular program, we need to understand how this actually gets turned into core and what this looks like at the core level. And at the core level, so core it's a simplified version of Haskell. It doesn't have all of the features of Haskell, so it works very well as an intermediate representation. So even though it does have pattern matching and function definitions and lambdas and things like that, it doesn't have type classes, and it certainly doesn't have arrow notation. This stuff all gets desugared into a simpler form at the core level. And so in order to take a look at what it actually looks like at the core level, I'm going to turn on this dump ds, which stands for dump desugaring flag. And I'm just going to make a very minor irrelevant change just so that this will get rebuilt. And then what we should be able to do is take a look at, oh, I forgot that GHC, this is Cabal doing this. Cabal isn't reconfiguring. All right, there we go. So now we should have this dump desugared. And it looks like this, which is actually not enormously helpful. So I'm going to write this in a simpler form. But basically what the arrow notation gets desugared into is this long chain of applications of the arrow composition operator, which in this case ends up in a let binding, which means it's not super easy to see. And also at the core level, everything is printed in prefix notation, not infix notation. So what this actually looks like, and I'm going to make a few minor simplifications here just to make it, a little bit easier to read, but it's effectively getting turned into this at the core level. So we have this loop function, which comes from the arrow loop class, and this R function, which comes from the arrow class, and then these are these two definitions here, which come from, I guess, just this module here. And in this particular case, the way that arrow notation is desugared, and this is not a video about arrows, so again, this actually doesn't matter that much, the way that arrows work, to what I'm going to be talking about here. But essentially, it just gets, this is just a forward composition operator. So this is just a pipeline of arrows where we have just kind of a recursive loop. This is kind of like fix, but for arrows, or mfix, if you're familiar with the monadfix class. And so it's going to start here, and there's going to be some data that flows through this pipeline, and there's a little bit of feedback. And again, it's not super important. But in order to understand what's actually going on here, we're going to need to expand these things anyway to inline these functions and take a look at what happens once GHC expands them and then is able to start trying to optimize them. Because the way that the optimizer works, there's a lot of different things that happen, but inlining is really what drives the optimization process, because GHC will inline things and then it will discover more optimizations that it can do based on just kind of having the functions be unrolled. And we'll see that as we kind of work through this. So the first thing that I want to start with is inlining these R functions. And so in order to do that, we need to look at what the definition of R actually is on this data type. And if we look at it, it's relatively simple. It's just this line right here. And so when I say inline the function, what I mean is, let me actually just put these side by side. What I mean is, in this case, R is applied to this argument here. So this argument is being substituted in for F right here. And so if we think about just replacing this with this, what we would do is we would take this and we would place it where F is, and then we can put this back in right here. And I guess I don't actually need these parentheses around the outside. And I guess it's this a little bit easier to see if I just don't do it in a comment. So you get a little bit of syntax highlighting. And so that's what this looks like expanded. We could do the same thing for the other use of R. Just put this in here and take the argument and substitute it in here. And so this is what GHC is actually going to be doing when it starts optimizing this program. It's going to start by inlining these functions, and then hopefully the idea is that after we inline all these functions, which, we've put inline pragmas on over here, so we're telling GHC to do it. Hopefully the idea is that some of the redundancies will sort of fuse away, and we'll end up with a nice clean program that looks very similar to this handwritten one. But of course, what we'll find is that in this particular case, that's not going to happen, but we have to walk through it ourselves to really understand why it's not going to happen. So the next thing that we're going to do is inline these uses of integral n. And so integral n is defined, where is actually integral n defined? It's defined right here. And so this is a little bit more complicated to inline because we've got these sort of auxiliary, can't pronounce words, where clauses, and we have these two definitions. But the truth is they're really just used here and here. So we can actually, in order to make this a little bit simpler to actually do the inlining to, let's just take these two definitions and move them in here. We're actually going to inline D and O into their use sites as well. So instead of having this, we're just going to put a lambda expression here. Oops. And I'm going to break this over multiple lines. And then here, I'm going to have this lambda expression here. And then we need to replace these equal signs with right arrows. And we can get rid of that. So this is a little bit easier because we don't need to be introducing like lets when we do our inlining. So once again, the way that the inlining works here is going to be relatively simple because there's only this one argument here, and in both cases, it's just a number literal. So we're going to be replacing v0 in each of these instances here. On the right-hand side, we're going to replace this v0 with 1 and 0 respectively. So for the first one, we can just copy all of this in here, and replace this with 1, and just the indentation. And then the same thing down here, but we're going to replace this with 0 and just the indentation. So at this point, we've inlined these definitions, and of course, nothing interesting has happened because the sort of spine of this computation inside of this loop is these composition operators. So at this point, it's really important that if we want things to optimize well, then once we inline these composition operators, this better expose some opportunities for us to clean things up. And so that's what we're going to take a look at now. So the next thing to do is actually inline this composition operator. So we need to take a look at what the composition operator is, how it's defined. And the definition of this forward composition operator is actually just a flipped version of dot here. This is the actual definition right here. And once again, we've got some big, complicated, right-hand sides here. And we have these where bindings. So once again, let's just move these definitions inline turn them into lambdas to make this a little bit easier to follow. So let's replace this with a lambda. And once again, turn that into a right arrow. And same thing over here. All right, so here's our definition now. In fact, in this particular case, I guess C is only used right here. I'm not actually entirely sure why Sarah wrote it in this particular way, but I'm sure there was a reason. But let's just remove that and remove this as well, just so that we don't have to do quite as much rearranging of things after we inline things. And also here, this is just constructing a pair and then immediately breaking it apart again. So you can turn this into two definitions, dv and b. Pull this out here. And I mean, this sort of rearranging of things is also a useful illustration of what the optimizer does, because it's actually very similar to what the GHC optimizer would be doing as well, inlining things and then simplifying redundancies like that, constructing a tuple and then immediately pulling it apart again. So once again, we have this B definition here that we can just inline in for B here. So we have dv and dw, and we can just put this in here and this in here. There we go. And so this is, maybe it's not as easy to read to a human, but it will make the amount of substitution that we have to do significantly simpler. So what we're going to do is inline this in for here, but instead of having, I'm just going to, because I still want to be able to compile this code, but just to make this a little bit less confusing, just going to flip the arguments here so we don't get confused and accidentally think the order is the other way around. Now, this is an associative operation, so it doesn't matter doesn't matter how we actually group it. It's required by the category laws to be an associative operation. But in this particular case, I think it'll be easier to just, I guess, start from the top and work down. Is that how I did it? Because I am pulling from a separate buffer I have open here of what I did. I'm not doing all of this on the fly. Just that would take too long. Okay, it looks like I actually started from the bottom, so let's do that. So let's just focus on this application right here. And I'm just going to pull this out, put it down separately here, so we can focus on what it would be like to inline the composition operation for this case. So once again, we're going to copy over the right-hand side and substitute in the variables. So in this particular case, v0 comes from this first argument to OD here. So I'm going to copy this, put this in here. Then D is used in a few different places. I guess it's only used in the one place. So D is just going to be this guy here. And that goes in right here. And let's see. So then O does appear in two places. So what I'm going to do, and this is actually essentially what the GHC optimizer would do, is I'm actually going to just create a let binding here to avoid duplicating code. And the GHC optimizer would also do something very similar, because GHC doesn't want to duplicate code and duplicate work unless it sees some good reason to do so. So let's just introduce a shared binding there. And then we have W0, which is this guy. So that's going to be substituted in here. Then E is this, and E is only used once, so we can just inline this directly. And finally P, which is this, and P is also only used once, so we can inline that in right here. Now, I realize that so far it might not be very clear where I'm going with this, but I promise that we'll get to something interesting. So for right now, I just kind of want to illustrate, okay, so now we've inlined these things, and indeed we actually do get a little bit of nice simplification from having inlined some of these things. For example, right here, we inlined this function, but this function is now immediately being applied to these two arguments. So right away, we can substitute in A for dv and v for the second argument, which is actually never used. And so we can actually just get rid of v in the second argument entirely. And then instead of dv, we can put a. So a can go in right there. And we can get rid of the whole lambda expression. And similarly, we can do the same thing over here, which is actually quite nice because both the arguments are totally ignored. So we can just take this and delete everything else. And we have something similar down here where we have a, which I'm now realizing, I guess, am I looking at the grouping here correctly? Okay, A is being applied to this. I was getting a little bit confused. A is being applied right here, so we can just substitute A in for Y. And there we go. And then we have this function here, which is applied to OAV. And at this point, I guess, where did this A came from right here? So we want to make sure that we don't get this A and this A confused. So although I think in this case, it's actually not going to be a big deal because this A is immediately going to go away. So we're just going to substitute this in here. And we don't need the parentheses here and here. And again, in this particular case, GC would probably introduce a little let binding for O here so that we don't duplicate this expression, but I'm just going to, though I feel like I've done something incorrect. Right, there was a second argument here, but it was just, there was an underscore, so this W is irrelevant, so we can just delete it. So let me make sure that I have done this more or less correctly. I feel like I've, okay, right, because O is bound right here. Yes. So we have these two uses of O, and the other use of O actually just disappeared entirely, which is quite nice. So we actually, O is now only used in this branch here. So let's actually let bind this as well. So let's introduce an intermediate variable called y so that we can pull this out. And again, the fact that we can just always do this is one of the nice things about Haskell being pure, is that in an imperative programming language, the difference between just calling something once and calling it multiple times might actually change the semantics. But one of the reasons that GC is able to do all of this moving of things around is that the purity of Haskell guarantees that it will always be the same. Although, of course, it might change the runtime characteristics, which is ultimately the goal. We're trying to make the runtime characteristics better. So now that O is only used in one place, we can take this right-hand side, and we can inline it in for O, and remove this let binding out here. Let me, once again, pull this back over. And then we can do a little bit more simplification over here, because now we have this applied right here to these two things. But once again, we need to be careful so that we don't confuse this V and this V, but it's okay because the variable names here were chosen by a human being. And so they have good reason to be the ones that they are. And we're substituting in V for V. So it'll all work out. So we can actually just pull this whole thing out and substitute it in right there. And so now this is our inlined version of this composition operation. And as we can see, we did actually get some nice cleaning up from this inlining. So to some extent, it was successful. And we can now take this whole thing and we can substitute it back in for this sub-expression, because this is the one that we were simplifying. And so now it looks like this. And there we go. So now, of course, we still have these two more composition operators to inline. So I'm not actually going to sit here and make you watch that entire process, because I don't think that would be terribly interesting. It's going to look very similar. So I'm just going to do that real quick and then we'll continue. All right, so I've gone ahead and I've inlined the composition operator into this first expression up here to get this. But I realize I don't want to do this one just yet, because I think it will be more visually useful to go ahead and inline OD paste first, because the way that things will work out, that's a little bit easier to do. So OD paste, I guess I'll go into a little bit about what's going on here. Basically, what we're doing is we're taking these two, and I mean, the truth is, I only sort of understand what this code does, but we're taking these two vectors and we're going to end up pasting them together end to end. And I guess, does paste come from, paste is just right here, so it's just appending them together. So once again, we're going to do a similar process to inline this. So we've got this f prime and q prime definitions, and it'll be a little bit easier to do this if we inline those into the places where they're used. So let's go ahead and do that. Here's the first one. And here is the second one. And now we can get rid of these. All right, so let's see. I'm going to be honest, I guess this is just, this slen function is just so that this is just providing the type level information. So I'm actually going to, well, I actually don't think I'm going to need to inline this to show what's going on here. So let's just leave that the way that it is. So the first thing that we're going to want to do is to inline this OD paste function into this bottom expression here. So once again, let's just, well, okay, right. This whole bit here is actually not necessary, because this is just doing arithmetic on type level arithmetic on natural numbers. This is just basically building up one of these S-now witnesses. So we can pretty much ignore all of this, and we can just pretend that it just expands directly into this. So, because this is always going to return S-nat, and then we just pattern match on it, so it just goes away. So we can just focus on this bit right here, although I guess, strictly speaking, I should be paying attention to the type level number arguments as they're flowing through here, which I think the first time I was looking at this, I wasn't really doing. One thing at the core level, which I guess is a little bit easier to understand now that we have explicit type application, but type applications are always explicit, although I guess I suppressed them, so that was sort of my own fault. But type level arguments are always explicitly passed at the core level. So maybe let's try and be a little bit more careful about that here. So in this particular case, OD paste takes two type level arguments. And really, I'm only really going to care about the N and M here, because the S is not particularly important. So let's introduce those to figure out what exactly they are supposed to be, so we can follow them as we run through this code. So N is the length of the first argument, and M is the length of the second argument. So if we look in this first example, here we have a v1 as the first argument, which is just a one length vector. So the first argument, N, is going to be straightforwardly 1, and then the second argument is nil, which is empty. So the second argument, type level argument here, is going to be 0, And the inverse is true over here. This first type level argument is 1, and this second type level argument, or no, the opposite. The first type level argument is 0, and the second type level argument is 1. And I'm going to do that here just so that it's a little bit easier to follow what's going on. And so again, we're pasting these two vectors together. So effectively, the end result ought to be that we have a 0 plus 1 or 1 element vector. Although there's a little bit of additional stuff going on here because this is written in sort of a continuation passing style. But we'll see what this simplifies out to as we inline it. So let's start by inlining this here. And again, we're going to be replacing this expression here. So this is a little bit, let me, to make this a little bit clearer, let's inline or just kind of put this here so we can see which variables correspond to which arguments a little bit more easily. And the arguments, type level arguments end up going in here for these two calls to paste. So this is where we're going to have this here, and I need to remember exactly what's going on here because this is just pasting the two arguments directly. So this is going to be n and m. But when we have cut applied over here, what are the n and m here? I should have remembered this before I took a look at this particular code. Well, so the arguments to this second function here well, I think the easy thing to do is let's actually just explicitly annotate all the types. So paste is applied to n plus m. And intuitively what we're doing is we're taking these two vectors and we're well, I guess it's applied to n and m, sorry. But it's going to result in a vector that is going to be n plus m. And then if we actually look at the definition of OD here, then the first argument has some length n, and then each of these two arguments is passed a vector of length n. So in this particular case, each of these will have length n plus m. But then when we also know that this paste call here, because this has to return another vector of length n, this paste call here is going to also have to return something of length n plus m. But f here, which is an argument to this function, accepts a vector as the first argument, as the second argument of length n, and then length m here. So cut is going to be still applied to n and m here as well. And then we're going to end up with a vector, another vector of length n, and v will have length n, w will have length m. And this then returns another vector of length n and m, and so then we're just going to paste them back together. So all of these type level arguments are going to be the same, and I assume, yeah, that's also going to be the case here, where this is just going to be n and m. All right, that was something I probably should have done before I started doing this, but so it goes. So let's fill those in over here as well. So we're going to have 1, 0, and 1, 0 right there, and then 1, 0 here. All right, great. So now let's actually do the work of inlining all of the non-type level arguments, which in this case, and I guess to be totally explicit, I'm also going to put those here. All right, so we've already inlined these, so we can remove them again immediately. But so v0 is the first term level argument. And in that case, that is, or in this particular case, we have this argument here. So v0 is just used here and nowhere else. We're just going to inline that right here and get rid of this. And then w0 is also just used in one place right here, so we can get rid of that. Then we have f and q. Now f and Q are each, again, used in exactly one location. So that makes this relatively easy for us. We can just inline F right here. And am I getting my parentheses right? Yeah, this is the expression. Inline this for Q. And so now, once again, we can do a little bit of simplification with these functions that we just inlined. So you can put in, again, we have kind of A in place of A, V in place of V, and W in place of W. But V and W are not actually used anywhere in here anyway. So we just pull this out and do this. And same thing here. We have A in place of A, V in place of V, W in place of W, which makes this all very, very simple. So let's just pull this out, replace that. And this sort of let is a little bit silly. So we can just pull out this Y binding into the enclosing let right here. And we end up with something like this. Now, in the case of these strict let bindings, technically I could just leave them alone, but at the core level, GHC doesn't have strict lets and lazy lets. Basically, the idea is that at the core level, case expressions are always strict and let expressions are always lazy. So I'm just going to make this look a little bit closer to how it would actually look in core. I'm going to turn each of these strict let bindings into a case. So this cut here would be case cut of, and then a pair pattern, and then the right hand side, we're going to do the same thing here. I'm going to say case this expression of this, and we end up with this, and then I'm going to do the same thing here. Just going to say case cut of pair pattern, and end up with this. And now I guess then we can reintroduce the let here, because this is a lazy let. And there we go. So I think this is all more or less correct. Yeah, it seems plausible. Now, this right here, where we are pattern matching on this tuple, we're immediately pattern matching on a tuple and constructing it right here. Excuse me. So we can replace this in for dv, replace nil in, man, can't type, in for dw, and get rid of that case expression altogether. And again, this is very similar to what the optimizer would be doing. And is there anything else we can do here? I don't think so. I think this is pretty much everything that we would get. So one thing that is worth pointing out at this point is that this, the results of this cut application, this pattern match on cut, V and W, are never actually used anywhere in the right-hand side. So in fact, we can actually just delete the entire case expression and just get rid of that, which is quite a nice simplification. And VW here is never used either, so we might as well just replace that with an underscore. And also, should be right arrows, not equal signs. But is there anything else that we can do to simplify this particular expression? In this particular case, I guess A is not used anywhere over here, but this VW argument certainly is. So we can't really get rid of that, although we don't use this W argument, which actually kind of intuitively makes sense, because if you look at this, we're cutting this particular vector into two pieces, but the right hand, or the right component of it is a 0 element vector. So in fact, this cut is relatively useless, but GHC doesn't know that, even though we do know that. And so that actually could be an instance where GHC is not optimizing this program particularly cleverly. But for now, what we can do is just mark the bits of things that GHC actually would know, and we can be fairly confident that, well, I mean, we know for certain that A is never used and that W is never used. So this seems like a relatively complete simplification of this this expression on the right-hand side here. So let's move that back in here. And we are starting to get there. We're definitely getting close, because some things have cleaned up relatively nicely, and now we can do the same thing for this expression up here. And once again, I'm just going to do this myself and introduce a small cut here so you don't have to watch me do all that again. All right, so now we have almost everything inlined here. I'm kind of ignoring this loop for now, but we do need to inline the composition operation one last time just to get both of these two things to hopefully fuse together in some nice way. So once again, that's going to involve this definition here, but this is going to be more interesting than the last couple times we've done this, because now we've got a lot more going on. So I'm actually going to continue to record this just so that you can see all of the gnarly details. So actually, I'm not going to put that here. We're specifically going to be producing another call to OD paste. And in this particular case, we've got V0 is this whole expression. So you can pull that out and put that here. And W0 is going to be this whole expression. So let's just pull that out and put that here. Then this is where things get a little bit complicated. So let's ignore O for a moment, and let's just focus on D, E, and P, because each of those things are only used once. So D in this particular case is this guy. So let's pull this out, substitute that in for D. Then let's break this over multiple lines to make this a little bit easier to read. E is this guy, so let's put that in right here. And P is going to be this guy. Let's put that in right here. Also, how am I? Just the random equal signs in places. All right, let's reindent this. Okay, so some things should start to clean up a little bit. Why do I feel like I've done something? Oh, I copy and pasted an extra parenthesis from over there. There we go. All right, so now we can also just put O in a let right here. All right, so let's see how some of these things clean up. So V is unused. It can just be deleted. Now we have an A here being substituted in for an A here. Again, the variable names make this all very convenient. So let's just replace this whole thing with this expression. Then for this function here, we have A being applied to this expression. So we'll substitute that in here. W is not used. So we can grab this whole thing, move this, put that in there. And let's see, down here, this, again, O call is very conveniently not used, so we'll just remove that. And then substitute in W for VW, that can go right there. And I need to make sure that I'm not accidentally confusing any variable names, but I don't think that I am. I think everything is still just fine. Because we have a V here, but that V, yeah, I think all the binding is correct. At some point, maybe I'll discover that I've done made some horrible mistake, but so far it seems fine. So once again, I now just have the one use of O, which is right here. And so A is this first argument here, which is unused. So we can just delete this argument, delete this argument. We're going to substitute in V for VW. Which is right here. And now we can substitute this in for O right here. This is going to get a bit messy. So maybe I should even leave this up here, I don't know, as a separate let binding. It's probably a little bit easier to read that way. Yeah, let's just do that. All right, so this is our mostly fully simplified expression. I'm ignoring that outer loop there. but it's pretty close. So now we do need to inline OD paste again, so that we can get everything pretty much totally inlined. But that's the last step, I promise, before things get a little bit more interesting. So once again, OD paste. Let's just put this here. So once again, we need to figure out exactly what the type level arguments are in this case. And I think in this particular case, they're going to be 1 and 1, because the result of adding 0 and 1 is going to be 1, and 1 and 0 is going to be 0. So now we actually have 1 and 1 as the two arguments here. So let's get to inlining. So we're going to grab this whole thing. I just think the indentation is the most laborious part of this entire process. All right, so N and M, we can just replace all of these usages with 1 and 1. Then V0 here is the first term level argument, so that's this, so we can put that in here, and this can go in here. And so at this point, we can start to see the patterns starting to form. We have this nested use of pastes, and in this, so F is this argument right here, which is used right here. And let's, again, do this in a somewhat less silly order. We're substituting AV and W in for AV and W, so we don't need to do any renaming whatsoever. We can just put this in right here. And same thing here. This can just get substituted in right here. It saves us a bit of unnecessary work. And so now we can clean some of this up. dv is going to be this whole expression right here. Put that in right here. And dw goes in right here. And again, we have this nesting of pastes. Oops. Which is very suspicious. And given that we're trying to optimize this program, seeing patterns like this is very, very helpful. It's a good indication that something is going on. So again, we don't actually use V or W anywhere, so we can just delete this. There we go. And then we can take a look at this side as well. So this V here is being shadowed by this V. So this V is never used. We can remove this. And I guess we can just convert this into a case expression. So now we also have this chain of cuts that's occurring. It's also a little bit suspicious. So A is used here, but this VW argument is not. So we can get rid of that. And then similarly, A is not used here. Only the VW argument is. So here is now our fully inlined and simplified body of this loop application. Now, at this point, this is when I sort of started to realize, okay, there's something interesting going on here that is not being particularly well optimized, because we're getting these long chains of pastes and cuts that are clearly just a huge waste of time. Because what we're doing, if you look at this, is we're pasting a bunch of nil vectors together with other vectors, which of course this is always going to be the identity operation. If we append a nil vector to any vector, then we're going to get that original vector back. And similarly, here we're doing a cut, and this cut is just slicing off a little nil component, which is then never even used. So this is a huge waste of time. And even ignoring this loop around the outside, this core expression is not getting as nicely cleaned up as we would like if we want all of this indirection to just go away. And so at this point, we might kind of start to ask ourselves, well, okay, what can we do about it? How can we improve this so that we don't end up with all of these redundancies? And this is actually a case where rewrite rules are extremely useful. And this is something that I feel like people don't have a super high opinion of rewrite rules, because it is true that a lot of the time they don't necessarily work super well. Because a lot of the time I think, I just closed that and I didn't want to. A lot of the time, rewrite rules that libraries use are they depend on things just kind of conveniently working out in a way that you can't rely upon. But in this particular case, something like this, where we see a paste or a cut where one of the two type level arguments is 0, that's extremely reliable. That's something that we can end up with this quite often. And so that's a case where using rewrite rules is actually likely to be fairly helpful and to be a meaningful improvement. So let's give that a try. And I already wrote a bunch of rewrite rules down here so that I don't have to just write them all out. But these are the ones that I ended up with. But let's just start with the simple ones to start. So let's take a look at, because these are the ones that I started with at this point, which is I realized when one of the two arguments is 0 for cut and paste, then we can rewrite it. And so let's just put these in here. So I want to explain a little bit about what this is actually doing, because this all needs to be indented by a space, I believe. GC is very particular about this. Or maybe just this needs to be indented by a space. I don't know. I've always found this particular the requirements here a little bit arbitrary. But what's happening here is that we're saying in any cut expression where we have some vector and the type of that vector is 0 plus m. Well, okay, I guess specifically what we're doing is saying, why do we need this for all here? Right, okay, this is the v argument. Okay, so we're saying that if we're applying cut to some vector v, and the type of v is 0 plus m, then we're going to have a cut application where the first argument, type argument is 0, second one is some natural number m. Then we can rewrite that just directly to a tuple where the left-hand side is nil, because we know, and the right-hand side is v, because we know that, you know, this is an identity that always holds. And similarly for paste, if we have paste 0 on the left-hand side, then a is always going to be nil. And we don't really need to worry about computing a at all. We can just drop it, and then we can just keep b. And so even if we have some, I mean, this is actually kind of a powerful rule. And again, this is taking advantage of Haskell's purity. Because a could be some arbitrarily complex expression that does some, you know, very complicated computation and just happens to end up producing nil as its result. And so if we weren't able to rely on purity in this particular case, then we wouldn't necessarily be able to just delete that expression because it might have side effects. But in this case, because this is pure code and the type of, you know, it doesn't even matter what the type is. It's clearly not IO being sequenced as something else. It's not used anywhere. So we can just delete it and it's no big deal. So if we now actually recompile everything, oh, I have my lack of replacing things with errors is now coming to bite me. Line 82, right here. There we go. All right, so let's take a look at that simple arrow program again. And what do you know? What was it before? Actually, let me quickly compare and contrast this again. Let me comment these out, rebuild. And so again, this is the example where we're just composing ID with itself 3 times. And so without those rewrite rules, we ended up with, just for that really, really simple program, 500 lines of core. But as soon as we add these rewrite rules and rebuild, then it goes down to, you know, being this. And this other junk appears, just kind of boilerplate that's only used by like typable instances. So we can just ignore all that. This is really what's being generated. And, you know, there's a little bit of code here for matching on these natural number witnesses. But for the most part, this is really nice. This is much, much, much better than we were doing before. So let's take a look now as well at the other, the assign arrowized program. And we can see that we're doing a lot better. I think before it was like 5,000 lines or something, 7,000 lines. And now we're down to 1,000 lines. But 1,000 lines is still a lot more than we want. Remember, the thing that we're comparing against is only about 500 lines. So there's still a little bit of performance being left on the table. And in fact, if we run the benchmark itself, let's just do that really quick, and that'll take a little bit of time. But we'll definitely have some improved results. All right, so I mean, that's really close, right? That's 71 milliseconds down against 51 milliseconds. So, I mean, at this point, I think this is really basically sufficient. But there is a little bit more that we can do to identify what's going on here and to sort of figure out why we're still ending up with about twice as much core. So actually understanding what's going wrong here is a little bit tricky because there's just, you know, quite a lot of code that gets generated, and it's relatively heavily optimized. You know, lots and lots of things have been inlined. So there's a few things that we could do to try and understand where things are going astray. And one of the things that we could try to do is we could add on this particular module, pass a GHC option, which is sort of the nuclear option, which is basically asking GHC, please just dump out an enormous quantity of information. So you can see basically every single step of the optimization pipeline. And one of the things that we see here very quickly if we do this, and so we can sort of see, just to kind of give you some overview of this file, there, I mean, as you can see from the scroll bar here, it's very, very long. We've got like 12,000 lines of core being dumped, but that's because this is a series of phases. So we've got like a simplifier phase 1, then float out, and this is just a bunch of optimization phases that GHC does. But we actually only really need to look at this first one here, this first phase of simplification. And right away, what we see is that we end up with something that looks like this, where we have a vector being passed in here that its size is 0 plus 0 plus 0 plus 0, and this long chain of zeros. And this seems a little bit suspicious because it certainly seems like this should be triggering our rewrite rule. So right away, we might ask ourselves, well, why isn't this triggering our rewrite rule? Where are we constructing a big goofy vector that looks like this and not ending up with things looking the way that we want? So in order to figure that out, although I realize, did I already have, okay, yeah, this was left over. I kind of forgot to remove this before I started recording this, but I had to add these phase control. I'm not going to go into the full details of how rewrite rules work, but this is basically just saying don't inline cut and paste too early so that we can actually have a chance for a rewrite rule to fire. I just kind of realized, oh, I didn't add those here, but I already had them. So to figure out why those rewrite rules aren't firing, we can take advantage of a feature of GHC, which is actually very useful in cases like this, which is a option called rule check, I believe is the name. Excuse me. Maybe I'll remember to edit that out, maybe I won't. So the way that rule check works is you pass it the name of the rules that you want to see sort of why they're not firing. And so in this case, I'm just going to say rule check cut and rule check paste. And now let's remove this, so that we're not getting too much output. And right away, we start getting some useful output. I didn't actually mean to rerun the benchmarks. So we can see that GHC is saying there are some situations where our rules are not actually matching. And so in this particular case, I mean, the output here is not super easy to read, but it's saying that arguments like this paste n equals 0 doesn't apply because arguments 1 and 4 do not match, and m equals 0 does not apply because arguments 2 and 5 do not match. Now, this is a little bit hard to see because we've suppressed the type applications here, so we're not actually seeing what those type arguments are. So let's disable suppress type applications and get Cabal to reconfigure things. And then I guess I also need to make a silly change to this module so that things will get recompiled. But there we go. Okay, so now we can see the actual type application arguments here. And what we can see is, okay, well, it certainly looks like something should match, but when we actually look at this, you can see that, well, our rule that we wrote over here says that either the first argument of, and this is for paste, yeah, so either the first argument has to be 0 or the second argument has to be 0. But when we look over here, we can see that neither of those things is true. The first argument is not 0 and the second argument is not 0. But, you know, we have this big type level arithmetic expression right here. And in some situations, like right here, I mean, in this case, neither of them are 0. Like this has a 1 in it and this has 1 in it. So in fact, this, if you were to simplify this all the way down, it would just be 1 and 1. But down here, we can see that this second argument is in fact 0 plus 0 plus 0. And GHC is not simplifying that. And there's various reasons as to why GHC doesn't simplify these things down. Because the way that GHC's type system works is this 0 plus 0 plus 0 plus 0 is actually a different type from 0. And to get into exactly like why those are different and how this all works is probably outside the scope of this particular video. If people are interested, maybe I can do that at some point. But these coercions here are, in fact, maybe just for illustration's sake, let me disable suppress coercions. We can actually see what those coercions look like. So this is naturally going to result in much more output, which is why normally it's very useful to suppress them. But if we go back up to this example, then we have some vector that's being, this isn't as interesting an illustration as I was hoping it would be. But basically, this coercion here is saying that when we add, this is not worth explaining. This is a bad idea. I take it back. I'm not going to go into the details. But basically, our rule does not match because those types, according to GHC, are not actually the same. So what can we do instead? Well, one simple solution is that we can add more rewrite rules. So what we're going to do is that in order to target this case, where we have some 0 plus 0, let's, I guess like this is the rule in question that we'd be using right here. So what we're going to do is we're going to say that if we have some application of paste, where, and I guess I can also grab the other one here. So if we have either an application of paste where the second argument is m plus 0 or 0 plus m, then we can actually just simplify that to an instance of paste nm. And in this particular case, GHC is smart enough to figure out that this is still a well-typed application because 0 plus m and m plus 0 are the same thing. And to, I guess, get into the full details, I would kind of have to discuss coercions and all of the internal guts. But it's actually not super relevant to what I'm talking about here. This is really more of a type checking thing than an optimization thing. So maybe at some point I can make a video that describes, oh, here's the type checking rules for type level natural numbers. But basically, GHC knows that this is still a well-typed application of paste. And so by doing this, we can remove those redundant zeros. And eventually, through repeated application of this, we can get rid of all of them and things will simplify down. So let me just grab all of this, all of these rules here, put them in right here. And so now if we rebuild this, then you can see that the only rule check failures that we have now coming out of this are cases where, in fact, we can't just delete the use of paste because it's actually doing work. We're pasting something of length 1 and something of length 1 in all of these cases. And so that's a significant improvement. So now if we take a look at this, that's not the right module. That's not the right module either. This one here, and look at the amount of code that gets generated. I guess the truth is we're still generating about 800 lines. It's only a small reduction, but it is some reduction. So this is still a minor improvement. We do still end up with these long wonky types here, but that's actually not a big deal. This is what really matters is the application sites, and those pastes are in fact getting removed. So if we now run the benchmark again and take a look at the difference, see how we did. Indeed, this is still about 50 milliseconds. That's good. That hasn't changed. And now we have about 57 milliseconds. And that is amazing, right? Because we started with about 250 milliseconds, and now they're, I mean, within a margin of error, basically. So that is a huge improvement on this program that we got just by adding, again, literally all that we changed was that we added these rewrite rules. But again, in order to know that that these were the rewrite rules that we needed to step through that entire process of the simplification ourselves and really see what was going wrong and where the pathologies were showing up. And so this is kind of a specific example. There's obviously many cases of optimizing a Haskell program where it's not going to be this beautiful and simple. But again, this was not a contrived example that I came up with just for this particular video. This is a real example that somebody else gave me, and that's why I think it's so wonderful, because it really does demonstrate this is what the GHC optimizer is doing, and this is how you can take advantage of it to improve the performance of programs like this. And if you can really distill a program down to the simplest possible pieces and really study it in this way, you can realize very nice things. And again, what's so great about these rewrite rules is that they are actually quite reliable, just due to the way that the GHC optimizer works. We're just really matching on the types. We're not even matching on the terms. So as long as, and the types are always going to be there. So as long as we know that one of these two types is going to be 0, then these rewrite rules can apply and we can get really good results. So this is, I think, a really nice example, and hopefully people found it helpful. I would love to do a little bit more of stuff like this. So let me know if anybody has any suggestions about things that you'd like me to do. And I guess I decided not to talk about this at the start of the video, but obviously, for those of you who've been watching the YouTube videos on this channel for a while, Richard Eisenberg has been doing them for a while, and unfortunately, he's recently left Tweag. He's doing very interesting new things, adding representation polymorphism to OCaml, which is very cool, but he's not going to be producing these videos anymore. So, I've kind of been meaning to do this for a while and do some videos myself, and I just figured, well, it's a good time for me to start doing that now that he's not doing anything. So I'm probably going to be doing them a little bit differently from what he was doing. In fact, I've only watched a couple of the ones that he did, but certainly any ideas that people have, feel free to leave a comment and I'll read them and maybe I'll do it. So thanks for watching this. I don't know exactly how long it's going to be, all things considered, but hopefully I'll see you in the future.